Welcome back, everybody. In this section, we're going to do the first part of section 1.2, which is on the language of algebra. So like the last section, this section is going to have kind of a mixture of different topics. So let's get started. So first thing is to look at constants and variables. Constants, of course, if you can just thinking about how the word sounds, are things that don't change, right? Like the number of inches in a foot is 12, and that always will be so, right? So just regular numbers, as we always have them, are constants, things that don't change. In an algebra class, what differentiates it from an arithmetic class is the fact that we're seeing variables. A variable represents well, there's two main uses in in math for variables. Main uses. One is to represent an unknown quantity, something that you don't know. Like if Farmer Bob had some chickens and he got 5 more chickens, and now he has 12 chickens. How many chickens did he have in the first place? Okay, well, thinking that through, it's going to be 7 chickens. If he started off with some, got 5 more, and now has 12. Okay, that would be one use of a variable. When you're in grade school, sometimes they'll use a little box to represent an unknown number. The second main use of a variable is to represent a pattern. So we all know that 3 plus 7 is 7 plus 3. 11 plus 8 is equal to 8 plus 11. And it doesn't even matter what the two numbers are. 273 plus 508, whatever that is the same as 508 plus 273. So there's a name for that rule, right? It's going to be the commutative property eventually when we get to it. But for now, here I've just written out a couple of examples. Instead of using actual numbers to illustrate the pattern, we could say, well, let's use symbols to represent those numbers. So we might write a plus b is equal to b plus a. So this is a second use of a variable in math to represent patterns. So the main uses we'll see are to represent some unknown number that we're trying to find, or to represent some number in a pattern. Frequently for variables, we'll use letters at the end of the alphabet, like X, Y, and Z. For the first case, the unknowns, and A's, B's, and C's from the beginning of the alphabet to appear in patterns. Although there's no official rule that says that, it's just kind of what how it customarily is. The other thing is that frequently when we have a variable that means something, we'll use a letter that is meaningful. If we're talking about the width of a rectangle, we may use a W. W for width, or H for the height on a triangle, or C for the number of chickens that Farmer Bob has. But often, if it's just algebra, we'll use X's and Y's and such. Okay, all right. The next thing that I wanted for us to look at is to make sure that we're clear on the difference between an equation and an expression. An equation has an equal sign in it, and it says the two things are equal to each other. For example, we know that 2 plus 3 is equal to 5. So this equal sign is saying, okay, this value on the left is equal to, or the same as, the value on the right. And you'll notice that on an equation is either true or false. If I ask you, okay, is it true that 2 plus 3 equals 5? You can say, yes, that's true. If I said, okay, well, is it true that 7 minus 0 is equal to 16? Of course not. That's definitely false. Okay, an equation has one of the properties it has is that it's either true or false, depending on what it says. An expression just evaluates to a value. It doesn't have a true or false attribute to it. So if we said 2 times 16, that's just 32, right? We can't say, okay, well, yes, 2 times 16. Now, what about it, right? There's not a complete sentence in there. If we have 7 plus 3 minus 1, okay, we can't say, okay, yes, that's true, or no, that's false, because we haven't said something about it. If we say, okay, well, that's equal to something, or is less than something, or greater than something, then it's more like a statement that we can tell whether it's true or false. An expression doesn't have a true or false value, an equation does. An equation is built out of expressions. The left side and right side are expressions. They're connected by an equal sign. and it's true if the two things are equal, and it's false otherwise. For some things, like these two, we can tell right now and for all time whether they are true or false. Other equations, ones that contain variables, their truth or false value uh, depends on the replacement value for the variable. For example, if I told you that some number, call it x, we'll replace x by that number. If we add 7 to it, we'd get 10. You can think about that through a little bit. You'll get there, okay, well, that number is going to have to be 3. This is true if we replace the x by a 3, and false otherwise. The point for now is that this one doesn't have the same truth or false value as the first two did, where it doesn't change. This last one depends on, it varies, right? Variable. It varies depending on what x is. Okay, but still an equation. And that differentiates it from an expression. We will also be considering inequalities. So we'll need the less than sign, greater than sign. And then we'll also have the less than or equal and greater than or equal to signs. Okay, these are also going to be complete statements where you'll be able to tell whether they are true or false, like an equation. So we can say that 7 plus 10 is less than 100. Yes, that's true. 6 plus 8 is greater than or equal to 1. That's true. It's not equal to 1, but it's greater than or equal to. Think about the meaning of the word or in there. The greater than part is sufficient to make the overall statement true. Okay, so this has been a little bit about constants versus variables and equations versus expressions. Some of the expressions that we're going to need will involve exponential notation, so I wanted to talk about that with you now. As you know, multiplication represents repeated addition. When we write something like 3 times 4 equals 12, you could take that to mean that if I added together 4s 3 times, that's going to give 12. That is, the multiplication tells us how many times the addition should be done. When you're working with exponents, an exponent tells you something about a repeated multiplication. So when we write 3 times 3 times 3 times 3 times 3, I probably had the wrong amount of 3s there, but that's okay. If you've got 5 3s like that and you're multiplying them together, we'd write this in the following way. 3 is the base. That's what's getting multiplied together. 5 is the exponent. That tells us how many times we're doing the multiplication. And so this is going to be the product of 3 times 3 times 3 times 3 times 3. And so that's 27, 243, right? I think that's 243. Double check, let me know if I got that wrong. But it is definitely not equal to 15, right? So 3 times 5 is 15, but that's not what this says. This is not saying we're multiplying 3 by 5. This says that we're multiplying 3 by itself 5 times. Okay? The exponent indicates how many times the base is used as a factor. Okay? In the language, we'll say often 3 to the second power, but most often we'll say 3 squared. 3 to the third power is 3 cubed. 3 to the fourth power, and anything higher than 4, we'll just say whatever power that is. The second power and third power, why those are called squared, has to do with area and volume. If you have a square whose side lengths are 3, how you'd find the area of that square, which is height times the width, that's 3 times 3, which would give you 9. That's why we say squared when we do 3 to the second power. Similarly, for the third power, we're finding the volume of a cube. If you have a cube with sides of length 3, then to find the volume of that cube, this one's going to look like a Rubik's Cube, right? It has 3 cubes in each layer and 3 layers, making a total of 27 cubes. That's why you get 27 when you multiply 3 by itself 3 times, and especially why we would say 3 cubed. Okay, so this has been a quick run through of exponents. Let me know if you need more about that. Okay, we talked about equations, a little bit more on expressions next. What an algebraic expression is a, this should say meaningful, not just random, meaningful combination of operations on letters, those would be variables, and numbers, that makes up an algebraic expression. So examples of algebraic expressions are shown here. 5 plus x, 6 times y, 3 divided by y minus 4 plus x. All examples of algebraic expressions. It turns out that it's pretty complicated to write down the official rules for what makes up a legitimate expression. But fortunately, with just a little bit of practice, it's going to be real clear to you what's legitimate and what isn't. For example, these are all algebraic expressions. We would never write something like 5 minus 3 plus divide x. Let's put a divide. No, let's just leave it like that. 5 minus 3 plus divide. Okay, this doesn't make any sense because you shouldn't have plus followed by a divide, and there's nothing following the divide. You wouldn't want to have a fraction with no numerator, but 3 for a denominator, and then a left parenthesis. And that's it, right? You would need another parenthesis, and the fraction would need something in the top, right? Okay, so with practice, you're going to get good at recognizing what makes up a valid algebraic expression. With multiplication, as you know from your earlier work, multiplication, there's a lot of ways of expressing it. Multiplying, frequently we put just two things next to each other. For example, 4 next to an x means 4 times x, and x next to a y means x times y. If you wish, you can use parentheses, 4 and then the x in parentheses if you like, but usually we try to do as little writing as possible. One thing worth noting is that from grade school, you may be used to using the cross for times, like 8 times 5 is 40. We usually don't use that cross for multiplication in algebra anymore because it looks like an x. And if we wrote something like this down here, 5 times x, it would look like 5xx, and that's really confusing. So pretty much you want to stay away from using the cross for multiply. Instead, use either just putting stuff next to each other, or a dot, or parentheses. Putting things next to each other, of course, only works if one thing's, in certain contexts, right? If you have a number times a variable, it's going to work. If you wanted to do 3 times 4, you have to put something, right? You can't just put 3 next to 4 because it looks like 34, so that's not going to work. If you have numbers with lots of decimals in them, like 3.14 times 8.6, you'd want to be cautious about using the dot because if you're speeding along writing, you don't want to get confused between what's the times dot and what's the decimal point, right? So you want to kind of think about that as you write. Maybe in this case with the 3.14 and the 8.6, I probably would actually write that using the parentheses for multiplication because I think it reads nicer and is less likely to be misinterpreted. Okay. What you do with expressions, the main thing is going to be evaluate expressions. What that means is we're replacing a variable in an expression by a number and then finding the value of the expression. That's what the act of evaluating of an expression for a variable is. As a quick example, if we asked you to evaluate 2x plus y, or x equaling 8 and y equaling 7, what that means, what the direction words are telling us to do, is to replace the x by an 8 and the y by a 7 and then compute. So 2 times 8 is 16, plus 7 is 23. That's what evaluate means. Turn an expression into a number using some given values of some variables. Okay, a little bit more practice using exponents. So here we want to write each of these using exponents. I'm using writing a product of 8s, and there are 4 of them. That would be 8 raised to the 4th power. B, we have 4 3 times. That'll be 4 to the 3rd power. And then this one is 10 to what power? 1, 2, 3, 4, 5, 10 to the 5th power. For this next one, notice that we have 2 different factors. There are 5s and there are 4s. There's 2 5s. That will be 5 squared. And then 1, 2, 3. Sorry about that. Zoom crashed on me again. Okay. All right, so let's continue. For the next couple of examples, we want to go the other direction with it. We're given a exponential expression. This one says to evaluate. There aren't any variables whose values are needing replacing, so we just want to calculate and get an answer. This one will be 9 times 9, or 81. Here, 4 to the 5th power. Okay, so that's 1, 2, 3, 4, 5 fours. Let me do this by grouping. That's going to be 64. 64 times 4 is 256. 256 times 4 is 1,024. So there's that. And then lastly here, 5 times 3 squared. Notice the exponent is just on the 3. So this would be 5 times 3, or 45. Notice that this is not going to be 15 squared. The 2 doesn't go with all of it, it just goes with the 3. So this is just 5 times 3 squared as we wrote. If we really wanted to make 15 squared, 15 squared would be 5 times 3, all of that squared. Here I've used parentheses to indicate that the 2 should go with both parts of it. Okay, so there's a little bit to this, having to determine which operation should go first. In this last one, 5 times 3 squared, we have to know, okay, should I multiply 5 by 3? We'll do the squaring first. Another example that illustrates that is here. We have 2 times 6 plus 3. You need to know, okay, well, is this 2 times 6, which is 12, plus 3, and that's 15? Or 6 plus 3 is 9. 2 times 9 is 18. Of course, they're different answers and they can't both be right. So the correct one is the first one. And that takes us to our next topic, which is the idea of order of operation. We have a set bunch of rules that tell us what order things should be done in. And that's listed here. Basically, you want to take care of operations inside of parentheses, square brackets or other grouping symbols first. And then when we get to it, fractions and square roots, starting with the inside and working your way outside. Then exponents are next, multiplication and division in order from left to right. That's important. Addition or subtraction in order from left to right. Okay, an important thing to notice is that multiplication isn't always before division. It's always left, whichever you encounter first as you work from left to right. The same with addition and subtraction. Addition isn't always before subtraction. Whichever is on the left matters. Okay, so let's try. 12 minus 10 plus 3, that's only addition and subtraction, working our way from left to right. 12 minus 10 is 2. 2 plus 3 is 5. Okay. For the next one, 18 divided by 6 is 3. 3 times 5 is 15. Okay, make sure that you read and understand those. If you have any questions about that, let me know. Okay, a couple more examples. This one has a multiplication, a division, and a subtraction in it. Multiplication and division are higher ranked than subtraction, so we'll do those first. 2 times 4 will be 8. 3 divided by 3 is 1. 8 minus 1 is 7. Okay, so the order of operations, we do grouping symbols first. Often people will say parentheses for that. There's mnemonics or memory aids for this. Parentheses, then exponents, multiplication and division, addition and subtraction. People like to say, please excuse my dear Aunt Sally, and memory aids like that to help remember this if you like. Grouping symbols, there are none here. Exponents, there weren't any. Multiplication and division, we did those first, followed by the subtraction. You'll notice that we did the 2 times 4 and the 3 divided by 3 in the same step. You can do that as long as they're separated by an operation that is lower ranked. Subtraction is lower ranked than the multiplications are and divisions are, so we're able to do the multiplication and division at the same time. Okay, so 7 for that. Okay, this one's good and long, so we're going to try this one. Take a minute, pause the video, and work your way through it, and then see what you get for an answer, see if you get the same answer as we do. Okay. All right, so I'm going to start with the grouping symbols. There's square brackets and also parentheses. They have the same meaning here, but often people who write textbooks and so forth use different types of grouping symbols just to make it easier to read, we hope. So at the innermost set, we have 10 divided by 2 is 5. That's being subtracted from 3 squared. Okay. At the beginning here, I'll show like a lot of steps. So all that happened in this first step was the 10 divided by 2. Okay, now inside the square brackets, we have an exponentiation, that is a power, and then the 5. We'll do the exponentiation part. That's going to be 9 minus 5. Be careful you didn't get 6 there. And then in the back, 7 times 3 is 21. I can go ahead and do that now because it's separated from the bracket by a subtraction, which is lower rank than multiplication. Similarly, 4 cubed here, that's separated from the other stuff by this plus sign, which is lower rank than the power. So I can go ahead and do the power now. The 4 to the third power, is that 64 or 12? Okay, you had better get 64 for that and not 12. Okay, 64 plus 4 minus 21. 68 minus 21 is going to be 47. Okay. All right, so hopefully you got that. If you didn't get that and can't figure out why you didn't get that, then let me know and we can go through it. Okay, so the next thing has to do with more at working with variables. This is about like terms and things of that sort. So let's take a look at that. So the first thing to do is to talk about what a term and a coefficient and things like that are. If you have a number multiplied by a variable raised up to a power, like 8x to the 7th power, or 4y cubed, or 11t to the 4th power, the number in front is called the coefficient. Okay, here the 8, the 4, and the 11 are called the coefficient. Each of these pieces, the 8x to the 7th power, 4y cubed, and 11t to the 4th power, are called terms. Okay, the expression 8x plus 3y, that's not a term. It's a sum of two terms. Terms are formed by multiplying things together, not by adding. So if at its outermost, it's a product of numbers, variables, and variables raised to powers, then it is a term. 8x plus 3y is instead a sum of two terms. Okay, so we defined what a coefficient was and what a term is. Before we go any further, I did want to mention this terms thing. There's a lot of times in math where we'll take and use a kind of almost everyday word from English and just give it a math meaning. Term has a couple of different meanings in English. It could be like you're taking like an anatomy class and you have to study all of the different terms or terminology, right? Somebody can go to jail and serve a term. Okay, that's yet another meaning for the word. In this sense, in this math class, this is what this means. A term is a product of numbers and variables raised to powers. Okay, so try not to be put off by the apparent redefinition of this word term. Okay, so let's just try a little bit of this first. In the first, it says, in these exercises, identify the coefficient of each term. So for 8a, it's going to be 8. For 6x cubed, it will be 6. For 13m, it will be 13. For 5r squared, it will be 5. Okay, so then in the next part, it says identify like terms. So we need to talk about what like and not like terms are. So like terms have the same variables. Unlike terms don't. So examples of like terms, 5x. Sorry, Zoom crashed again, yet again. All right, so if we had 4y cubed and 11y cubed, those are also like. Let's do one with two variables in it, 7ab and negative 2ab. The variable parts are the same. Unlike 7 and 2x, 7 doesn't even have an x and 2x does. 3x and 4xy both have an x, but the first one doesn't have a y and the second one does. 6x and 6y both have a 6. Nobody cares. One has an x, one has a y. They're not like terms. 7x squared y and negative 3xy squared. Those two are not alike. One has a 7, one has a negative 3. That's not the part that matters. What matters is the variables. X squared y is different from xy squared. While they both have x's and y's, and the first one has the x squared, the second one has the y squared, and that makes them different. If you think about how they sound, that can help you decide. X squared y should sound different from xy squared. But over here on the ones that sound alike or that are alike, they should sound alike. 7ab minus 2ab. Those sound the same and they are in fact the same. Okay, so that's what like terms are. Okay, so in these problems, we are to decide what the like terms are. So in here, it looks like 8x cubed and x cubed are the same. And then the 14 and the 5 are the same in that they have just numbers and no variables, so they are the same. Let's do just one more of these. Let's do 147. 9a, is there something else that is just a's? No. A squareds, anything with a squareds is going to be alike. No, not having much luck here. There are two terms that have b squareds in them and two terms that are just plain numbers. So the ones that are yellow are alike, the ones that are blue are alike. Let's do one more because those are kind of fun. Let me first see if there's anything that is, let's see, what should we get? Squared, r squareds. 25r squared and 4r squared. Both of those have r squareds. I see a couple that have just s's. There's 10s and 3s. And that's all that's alike within these. Okay, so in the next part, we're to identify the different terms in each expression. 149, one term is 15x squared, one term is 6x, one term is 2. It's just the three pieces that are being added together. So we should know what terms are, we should know what like terms are. And then, okay. All right, so if you have any questions on that, what makes up terms, what makes up like terms, let me know. Okay, moving on a little bit. Translating English phrases to algebraic expressions. In our textbook, you'll see a table of words that correspond to different meanings. For example, sum means addition, difference is subtraction, product is multiplication, and so forth. So what we're going to try to do here is translate each of these expressions from English into math. So here, let's try 163. Difference means subtraction. So we'll have 14 minus 9. Difference of 14 and 9. Product is multiplication. That will be 8 times 7. Sum should mean addition to you. That's 8x plus 3x. Okay. Notice in here the directions are just telling us to translate these phrases into algebra. We're not actually evaluating them. In case you're wondering why I just left 14 minus 9 as is instead of making a 5 there. Okay, so let's see, what else would be good? We didn't do quotient yet. Quotient is division. That's 36 divided by 9. Last couple are interesting. 8 times. 8 times what? 8 times the difference of y and 9. And notice this one has 2 operations in it. You want to make sure that you read this so that you can get 8 times and then in parentheses y minus 9. Okay, 174 is going to be the same. All right, that's it. All right, so now what we want to work on next is combining like terms. We saw a minute ago what like terms are. We've taken a break from it, and so now we're back to thinking about it. Like terms, remember, are terms where the variable piece is the same. So 10x, let's try 153. 10x plus 3x should be 13x's. You can think of this as you're adding up anything that is alike. If you have 10 grapefruits and 3 more grapefruits, that's a total of 13 grapefruits, okay, where x is a grapefruit. Okay, keep in mind that we can only add things that are the same. If they're not the same, they cannot be added. Let's try 155. 4c plus 2c plus c, that is 7c. Okay. In 157, there's a couple of things that are different. 7u and 3u will make 10u's. And then 2 plus 1 will be 3. Notice that there are some unlike terms there, so it's not 13, it's not 13u, right? We're able to add together the u pieces and then just the number pieces. Okay, let me try 159 next. I can see here there's some that have just a's and some that have just numbers. So there's 10a plus 5a, that's 15a, and 7a, that will make 22a's. Okay, now let me add the number pieces. 7 minus 2 is 5. 5 minus 4 is 1. Okay, in case you're wondering why I'm doing this underlining, the underlining is to make sure that I didn't forget one. And I'm trying to color code it to help you see what I've got going on. But I'm underlining it to make sure I didn't forget any. I also, you've probably had other teachers where they've crossed stuff out. I don't like to do that because I think it makes it harder for you to read if you're following along. Okay, so that's why I'm not doing that, instead making the marks underneath. All right, so let's try this big one, 161 underneath. Pause the video, take a second, try that, and then we'll see how we did. Okay, I'm going to start with the squared terms first. There's, it looks like a total of 17x squareds. And then I'm going to take plain x's next. There are 12 plus 8, or 20 x's. And then lastly, numbers, 11 plus 5 is 16. Okay, and that should do it. All right, this takes us to the end of this first part of section 1.2. We'll have more to do, but it'll wait for now. Let me know if you have any questions, and then have a great day.